number 4. All right, let me share my screen. All right, so can you guys see my screen?
Yeah.
All right, so the problem is called Bella segment tree. So Nate is taking a CS3 final exam and finds a really hard question Miss Lorena put on the exam to troll her students. And here's the problem. So you're given n elements, A1, A2 to an, and you're asked to answer several special queries in the form ij. Miss Lorena wants to know for each special query the number of unique numbers in the subarray A of I to A of j. So Nate can't solve this problem when Miss Lorena isn't. So Nate can't solve this problem. So when Miss Lorena isn't looking, Nate peeks over at Bella's desk and finds that Bella has printed a segment tree implementation on her desk. When Bella goes to use the restroom, Nate steals the paper printed with Bella's segment tree implementation. And the problem is Nate doesn't know how to use a segment tree, and he wants you to help him. So there is a segment tree solution, and I've noticed that most people who solve the problem use the bit, which is pretty similar to a segment tree, at least in terms of this problem. But the solution I'm going to give to you today, or present to you today, actually isn't a segment tree. Yeah, so I'm basically just it's actually a less efficient solution, but I just want to use this problem as a teaching example for that for this new topic I'm teaching you. All right, so first, all right, so let's just go over the constraints. So n is 30,000, and the number of queries we have is 200,000. So we're first just going to go over a naive solution. So a pretty easy naive solution is just to iterate over every query. So this is like if this is like the left boundary of the query and this is like the right boundary of the query, we would just use a for loop to find the number of unique elements for each query range. So that would take O of n times q, because for each query we have to loop over, we can pause, at max we'll loop over the entire array if each query was like from 0 to n. So I'm just going to code that up first. As you can see here, I've already included all the constants. Oh yeah, by the way, I'm actually using C++ this time, and that's because my snippet was already in C++, which I will so I have a snippet for the algorithm that I'm going to teach to you guys today, and I have it on my GitHub. So I'll share that with you guys afterwards. But for the most part, this code should be very easily transferable to Java. So I'm going to start just initializing my variables. And then we're going to input n and q. Just n right now. And then we're going to input all the array A. And let's let's initialize the array A. And then let's input all the queries. And actually, for the sake, so I'm gonna code this naive solution in a way that actually it wouldn't be like the regular way you'd code this solution if you're actually trying to code the naive solution, but I'm coding it in a way such that I'll make it easier to see the actual solution. So I'm actually going to create a query class, which would be completely unnecessary if you're just trying to use the naive solution. So this part that I'm writing up is just a simple comparator. It's just like when you want to store like an array list or something in Java. And then, yeah, if you're storing a class, you need to like write a custom comparator. Sorry, I can't type today. Oh shoot. Actually, I'm gonna leave this part. Actually, okay, yeah, I'm gonna leave this part out for now because it has to do with the next part or the actual solution. Okay, so now we're just gonna so this is our query class, and now I'm just gonna create an array for to store all our queries in. And I'm actually gonna so in the problem the indices I and j, they're one indexed, so to make it easier I'm just gonna make them 0 indexed. And this and this format in C++ is basically a quick way to make a struct. So it'll be equivalent in Java to like writing like new query and then putting parentheses in there. All right, so I'm actually going to put this in a method called solve. So most of the algorithm will just be in this method called solve. So the way I'm going to the regular way you do it, if you're just writing this naive, is to just write a loop that goes from the left bound to the right bound. But for the sake of our the actual solution, I'm actually going to implement it in a different way. We'll have two global variables. One is like a left pointer, and one is like a right pointer. And initially, when you're starting a new query, they can just be anywhere. They'll probably be left over from the previous query. And then what we're going to do is so you also keep a variable called it isn't a variable. It's like you keep the information within this current range about how many unique elements is in there. So when we have a new query, what we're going to do is we're going to shift the right global variable and left global variable to match our new query bounds. Okay, so I'll code that up right now. So I'm gonna write the two. So first we're gonna initialize the two global pointers. So I've initialized them, so they're currently not covering any range. And then we need something to keep track of the information. So basically, how many like unique elements we have between these two global pointers. So we're gonna do that with a frequency table called counts. So this would just be like counting how many like what's the frequency of an element within this range. So if there's like two twos, then count 2 would be equal to 2. Okay. So then we're gonna loop over all the queries. And then for each query, we're gonna get the left and right bounds. Okay, so I'm actually going to declare, I'm just going to write 2 more methods. So these methods will be called void add, and then this will just be like, so it's going to be add, and it's going to be another one called remove. So add and remove are when we move these global left and right pointers. So like for example, when we move this right pointer over 1 to get closer to the query right pointer, we're basically adding this this element into this range. So that's what the add does. The add basically adds this new element into the range, and then updates like the unique count accordingly. And then the left pointer does the same. So like when you move the left pointer over 1, you're basically deleting this element from this range that we currently have. Okay, and again, yeah, we actually need one more variable up here called total. So total would be like the total number of unique elements that is currently between our global left and global right pointers. So add would be like we'd increase the frequency of whatever element is at this point. So this is the element that's at the current position to the right, and we increase its frequency in the frequency table. And then we check if the frequency table becomes 1. So if it becomes 1, then we know we have a new unique element. So then we increase total. And then in the remove method, so we're actually going to remove or decrease the frequency of the element at position, and then we're going to check if this current frequency value becomes 0. So if we know it becomes 0 after we decreased it, that means originally it was 1 or more. It was originally 1 before this, and then dropped to 0, which means we just lost a unique element. So then we subtract that from total. All right, so now we have these two methods. Now we're going to go back to our main method, solve, and then so basically going to move the left and right pointers. So the first two methods, so this while loop would just be like while this current left pointer is to the left of the query left pointer. So in that case, we need to keep removing elements from our range. And I'm kind of to make it more clean, I'm kind of doing this thing where I'm doing this post increment. So it's basically equivalent to just using the current value of cur_l and then incrementing it later. But I'm doing it so it looks pretty clean. And again, if the global L pointer is actually to the right of L, then we need to actually so if the global point if this global L was actually to the right of the query L, we actually need to move this way, and then we'd actually be adding elements instead of deleting elements. And the reason why I'm doing a pre-decrement this time instead of a post is because we actually want to delete the we actually want to delete the element that we actually want to add the element that it's moving to, versus when we remove something, we want to remove the element that we're currently pointing at. So that's why there's a difference here. All right, so I'm just going to do the same thing with the right pointers. Yeah, notice it's the opposite for the right pointers. Okay, so yeah, and then also for the sake of making our for the sake of our actual solution, I'm actually going to include this additional variable called answer and array, and it's just going to store the answer for each of our queries. So then we're gonna have to, we're just gonna, so after this, we after we do our updating here, we know total is just after we do the updating here, our global L and R will match our query L and R, and then after that, total will reflect the answer for that query. So we're just gonna enter in the answer for this query. So this would be queries at I.index total. Okay. So I believe, okay, actually, yeah. So we have to print the solution now. Okay, I keep clicking Control S. So I think this should work as a naive solution. It should time out, but it should get some cases correct. Oh, okay, yeah. Okay, I'm just curious. I'm gonna see how many test cases I can get right with this before it times out. Oh, I got 2 test cases before it timed out. Okay. All right, let's copy the solution back in here. Okay. So now I'll go over the actual solution, and this is so the actual solution is this technique called square root decomposition, and basically, it's actually the code is actually pretty similar to the code we currently have, but so the main gist of square root decomposition is we're gonna break up this is so if we have an array, we're gonna break up the array into square root blocks. So let's just say like the square root of n is equal to 3 for now. So then this will be like a block, this will be a block, and this will be a block. And then here, I'll just make it so there's an extra space right here. So if you have something that's not like a perfect multiple, so if n is like not like a perfect multiple of 3, that's fine. The last block can just be like, it doesn't have to be exactly 3, it can be less than 3. Okay, so then now we're going to use the same strategy above, but instead, so like the exact same algorithm we've coded up here before, but before we do that, we're going to actually sort the queries by their block first and then their right pointer. So I'm just going to code that in here first. So so that's why I wrote this query class, and so I can do sorting. So now we're going to write the sort comparator that I was writing earlier. Okay, so first, we're just going to check if the two, I need to write this new method above here called block. So block is basically just going to tell us like which block we're in. So this would be like block 1, block 2, block 3, or I actually zero indexed it. So this is like block 0, block 1, this is block 2, block 3. So a simple way to identify like which element is in each block is just, so you can have a pretty easy method. Yeah, so it's actually just a one-line method. You just return like the position in the array and divided by like the square root of n. Okay, so now we can use this method in our sort comparator. So first we want to sort it by like which block it's in. So you guys who are like more advanced at coding, you guys know like usually when you write sort comparators, you have to first check if like the first condition you're comparing them to is equal to each other. So if they're in the same block, then we're gonna do something else. Okay, so this will just be the case for now that yeah, so this is the case of their blocks are equal, but the first condition, yeah, is to compare them based on their blocks. So if they're not equal, then we'll just return the one in a smaller block. And then if they are equal to each other, we're going to return them by their right indices. So we're just going to sort them by the query's their right boundary. Okay, I think that should be my that should finish the sorting comparator, and then yeah, so let's sort it. Yeah, so right after we input the queries, we're just going to sort the all the queries. Okay, so now that they're sorted, so in fact, if we run this code right now, so all we've added so far, all we've done is just sort, add a new sort and just reorder the way we did the queries. Otherwise, the solution is basically the same as the naive solution we just did. Okay, so you might be surprised, but if we run this code, okay, there's not supposed to be an error. So where's this error? Oh, okay, yeah, there's not a vector. Okay, so Yeah, this is just C++ sorting syntax, so like it shouldn't be that hard to convert it over to Java. Yeah. Okay, so pass the sample, and actually, if we submit it to the judge test cases, okay, that should not have happened. Let me look at my code. Okay, and then we copy this back in. Oh shit, oh yeah, this should not be n, this should be a q, because q is the number of queries. Okay, let's try this again. Okay, as you can see, we got all of them correct, and all we did, the only thing we changed from the naive solution was just adding this extra sort comparator, adding this block thing, and sorting. So basically all we did is just reorder the queries, and apparently now the naive solution works. So you guys might be wondering, okay, how is that possible? So I'm going to show you guys how this simple sorting changes the big O runtime. Okay, so since we split up the queries into blocks, so we're initially we're basically going to process all the queries based on like the left index in which block the left index is in. So basically going to process each block at a time. So within, all right, so if we write a big O notation, we know the queries only move, the left index or the left pointer of each query only moves. So actually, forget what I just said. Right, so we know initially all the since all the queries are sorted by their block, the block of which like their left pointer is in. We know like, so let's just say in the first block, this would be like a bunch of like pointers from queries, right? And then they're not necessarily in order. This could be like query 0, query 1, query 2, query 3, query 4, query 5, right? So like in a naive algorithm, we would have to move this left pointer back and forth to all of these, right? So it'll start at 0, then it goes to 1, then it goes to 2, then it goes all the way to 3, then it goes to 4, then it goes to 5. So you can see every time it can basically move up the like queue, right? I mean not queue, like the block size, right? So basically for every left pointer, so there's q left pointers, and for each of those left pointers, we know they have to move at most square root of n, because this left pointer, all it's going to do is just keep moving inside this block, right? And then and that holds true for every single block. So every left pointer is in a block, and every and for each block, the global left pointer is only going to move square root of n time. So then that takes care of how much this left pointer moves. Now we have to look at how much this right pointer, this global right pointer moves. So the global right pointer, so if we look back at our sort, we sorted the right pointers just in if the blocks are equal. So within the same block, right? We sorted the right pointers by we sorted them ascendingly. So like from like least to greatest. So like all the right pointers will be something like this. So these will actually be like in order. So like we know our right pointers, so like these will actually be like 0, 1, 2, 3, 4, 5. So we know our right pointer, unlike the left pointer has to keep oscillating in this block, but our right pointer will not. It will keep moving for once it goes to this one, it'll move on to like 1, then it'll move on to 2, move on to 3, move on to 4, move on to 5. So you can see at most the right pointer can only move length n, because like the array is only in length n. And yes, so basically for each block, the right pointer only moves n times. So how many blocks do we have? We have square root of n blocks, and for each block it moves n time. So that is n square root of n. So basically right there, we've already taken care of the asymptotic runtime for the global L and the global R. So this is basically our big O notation, big O runtime. But then if you want to be more strict, you can also include sorting it, which is just queries q times log q. So this is the yeah, so you can see from the simple sorting, all we did was just sort. That's the only thing we changed from this naive solution. And we've managed to bring down the solution from n times q to this, which because n is only 3 times 10 to the fourth, this solution works. So one way, all right, wait, let me get a sip of water. All right, so one strategy, like when you guys are solving constant stirring problems, one hint that a problem could potentially be square root decomposition is if n is only 10 to the fourth, because if n is 10 to the fifth, then square root of that would be like 10 to like 2.5, which and then that, so 2.5 times 10 to the fifth would be like 10 to the 7.5, which is like a little on the boundary of some judges. So usually the highest n can be during a square root decom problem is 10 to the fourth. So that's could be a giveaway for some problems. Yeah, and then another thing I want to mention, so like many of you guys solved it using segment tree, which is only like O of like n plus q log, I think it's like log n. So you guys are wondering like, oh yeah, what's the point of the square root decomposition solution if like I just have a segment tree that can do it much faster. So for this problem, the segment there really isn't any point because segment tree can beat square root decomposition. But for some problems, you actually can't use you can actually only use the square root decomposition problem and not the segment tree problem. So for example, a problem like finding like the mode of a segment. All right, so like for finding the mode of a segment, you can't really combine like, so for range queries like segment trees a bit, you have to combine like a left and a right, and then you can't really do that with the segment tree, but that is an issue using square root decomposition. So yeah, does anyone have any questions? All right, if not, you guys can always ask in the Discord, and I think either Victor, are you posting next? Do you have next week's problem set link?
Oh yeah, sure. I will link. I will link the 1 sec. All right, the link for next week's contest is in the chat now.